Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellyn, Illinois. And this video today is the 2021 Advent of Code, Day 14 festivities. The problem is called Extended Polymerization, and this is part 1 of 2 parts as always for the Advent of Code. And I've only gotten part 1 done, but it's 12:30 in the morning, or late night for me, and I'm not sticking up. I have an idea of how to solve part 2. But I'll work you through part 1. So you have polymerization, something that actually have a research paper written about the LSARLAF polypeptide chain. It has been probably over 20 years since I've thought about this. About 20 years, and oh my goodness, yeah. So it had to do with blood platelets, and it was when I did this at Benedictine University. Don't remember much more. But that's not necessary to solve that problem today here. So we're starting with this chain of letters, N, N, C, B. And basically, for every 2 characters that are adjacent as we go across here, there's the capability of jamming in another letter between it all. And so that's how that you can do that. So basically, they cover, there's what, 4 different ways. Let's see, 4 times 4. There's 16 different ways. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different combinations here. So every one along the way will give me a new character that I jam in the middle as I go. And so the length of this thing will always be 2 times the current length minus 1, because there's always going to be minus 1 links between the letters here. And it looks like there's always going to be the correct number of combinations, so there's no dead ends or anything like that. That's what it seems like from my puzzle, from my input anyway. I got part 1 to work. And so that means, as they say, that basically 4 becomes 7, 7 becomes 13, and then becomes whatever it is. 7, blah, blah, blah. Yeah, 7 is like 13, then 25, then 49, then 97. And you can see, just, again, 2n minus 1 for the size of each generation. But then, when you go through X number of generations, the problem is asking you, take the largest number of letters, the letter that's in there, the largest number of times in your peptide chain, and subtract it from the one that's the smallest, and what do you get? And so let's say 1588 for that, but let's describe the code, and then you can see that my solution will match up with what you got here. So the data comes in looking like this. The first line is the starting string, the phrase is what I call it, and then the second string is empty, and then everything else goes from there are all of the, I call them, the conversion factors. So I basically get the phrase right off the first line, strip off the new line, read a few times, and start a dictionary for this, so that I go, oh, the left-hand side the left-hand side is the key, and the right-hand side is the value. So dictionary map, same kind of basic idea, hash map or whatever it's called. And so we're ready to go. And so it just does that, boom, 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 boom. The left-hand side of that gets the key. The right-hand side gets the value. And we're ready to go. Boom, boom, boom. We're fine. We're down. Okay, out of this. So then all we're doing here, or all I'm doing here, is I'm creating a new list, or a new string for every generation. And so I start with whatever nn, or whatever. In this case, it's a big one here. And all I'm really doing is going ahead and, for the first part here, I'm going ahead and literally creating a new string, inserting as we go, and creating the string character by character by character. So if NN comes in from our original sample data, then I know that, and just the way things are working here, that I know that I have to put the N in first. That's what I have to put the N in first here. And then I have to find the character that goes between the N and the N, and then basically draw that in there, and then I can put the other N in there. And that's basically how the loop works. Take 2 characters, take the first 2 characters, oops, don't do that, and then find it in here, get me this guy, and then print out this character, then this character, then this character, and then move on to the next one. And now CP becomes PS. And then you find PS in here, wherever PS is, and then you know the next 3 characters to go, and so forth and so on and so on. And then basically you're all ready to go. So now when you get to this part, you have a string with all the characters in it, And now we have to basically, I don't know if I can take this one step further. I feel like I can do this all in one line, but I haven't, but I got to work it in three. Is basically to take the dictionary, convert it into a set, and then add to it all of the characters one by one throughout the whole phrase. I feel like there's one thing I'm keeping away from it. But say take the string, convert every character from it into a set, and then from that generate all the keys and set the values equal to 0, because I'm going to be taking one by one. I'm going to go, oh, add an N, add a C, add a P, add a V, add whatever, and then at the end of the day, I'm going to have a dictionary that maintains the keys, which are just single characters, and then how many times they've been found in that string. And then now that I have that going for me, then I go through and I find the maximum element, the minimum element, and print it out. So all of that put together gets me to here, which is 3,697 is the difference between the largest number for a single element versus the smallest number for a single element. So 3,697, whoop, gets me here 3,697. So part 1 is complete. If you know a better way, I'd love to hear it, so please comment below. And part 2 is where you, and I like these kind of problems where you realize that your initial method works great for small values, but will absolutely not work for anything of substance. There's not even a hint of me to even make an effort. 40 steps is going to take, it could take a week, or I don't even know, it could take a lifetime. And I don't even know if, maybe it won't even take that long, because it'll probably crash. Yeah, now that I think about it. What is this number? This is 219 billion. We can't store that, we don't have enough RAM for that, right? That's just for one element. So yes, this can't be done with the algorithm I have currently. So I'm going to have to convert the ever-increasing string into some other kind of data type that maintains values. I think I did this kind of thing in a previous video for this advent of code. These things all just sloshed together, so I do not remember which day I'm thinking of. But once that's done, it should be a pretty quick, it's one of those things where you think it could take an infinite, a ton of time, but it'll turn out to be a very simple amount of time at the end of the day here. So thanks for sticking it out with me. As always, I hope to have part 2 done sometime tomorrow. It is finals for us here at the College of DuPage as I do this, so I have to absolutely work on my work stuff first, but that doesn't mean I can't have this problem mulling over in my head during the day like many of you guys do the same kind of stuff as well. All right, take care. Thank you. See you later.